Matrices are extremely useful and extremely powerful, particularly when they're used in computer science. In fact, you see them used all the time, particularly now that graphics are becoming higher resolution and higher definition, such as 2D to 3D and so on and so forth. When you see them in computer science, they're also called arrays. So if you are doing some coding and it talks about an array, what it's talking about is a matrix. So let's look at a matrix and kind of look at its basic parts before we actually do anything with them. So let's say we have a matrix M, and I'm going to fill in matrix M. Alright, so this is matrix M. And we'll notice that matrix M has a lot of different pieces to it. It has a whole bunch of different numbers. So when we were talking about matrices, matrices have rows. And rows are these three guys that go across. So think about it like a row in a movie theater. And matrices also have columns. And the columns are up and down, the vertical parts. In this case, we have 4 columns. And you can remember that because they look like the columns on a house. When we talk about the size or the dimension of a matrix, the dimensions of the matrix are always written out in rows by columns. So I would say that matrix M was a 3 by 4 matrix. That means it has 12 entries in it. It has 3 rows and 4 columns. And this is, you can kind of see why they're so useful, is because you can store a lot of numbers in a matrix, and then when you're coding later on, you only have to refer to matrix M. You don't have to write out all of those different numbers. Now, when we're looking at our matrix and we see we have a 3 by 4 matrix, we also have all those little individual entries. Those individual entries have addresses. So if we were talking about matrix M and we said, okay, well, what's M, let's say 2, 3. What that's asking you for is, what is the entry in row 2, column 3? So M, 2, 3, we would go to row 2 and column 3, and we would see that the entry there is 0. So M, 2, 3 is 0. So I could say, well, hey, where is 11? And 11 would be, if we look at that, it's in the 3rd row, and it's in the 2nd column. So the address for 11 is M32. We need to know about all those different parts because we're going to be using them to do some calculations with our matrices. Matrices are good on their own, but we combine them with other matrices, adding them, subtracting them, multiplying them. We need to be able to identify each of those different entries. So here we have a matrix, and we call this matrix A. And let's just apply those basic principles to it and find some defining characteristics of matrix A. First, we want to think about its size. Matrix A has 3 rows and 2 columns. So we would say that the dimensions of matrix A, it is a 3 by 2 matrix. Now we could talk about all those different addresses or all those different entries within matrix A as well. So we could say, okay, let's find A2, 3. A2, 3 would be in row 2, column 3. But wait a minute. We don't have 3 columns. So there is no entry there. You could say no solution, but there's no entry at A2, 3. Now, we might have to find A3, 2. Now that means row 3, column 2, and in this case there is an entry there, and it's -6. And let's say, where's 3? 3 is located in the 1st row, in the 1st column, so its address is A11. And again, these little features, these addresses, are really important, particularly when we're talking about coding things. This is how your calculator knows how to do things with matrices. This is how your computer knows how to do things with a lot of graphics and other parts of code. There are two main types of multiplication that can be done with matrices. You can multiply a matrix with another matrix, and that is kind of complicated, so we're going to save that for a whole other video all by itself. And the second type of multiplication, though, is scalar multiplication. Scalar multiplication just refers to multiplying a matrix by a constant. And you can do this just like you would do any other multiplying by a constant, like you would multiply a variable by a constant or another constant by a constant. So let's say we were going to have a matrix here. I'm going to 1, 2, 3, 4. And an example of a scalar multiplication with this matrix would be, hey, let's find twice this matrix. Let's find 2 times this matrix. When you're doing a scalar multiplication, it's really pretty easy. All you do is multiply each of the entries by that number. So in this case, we would have 2 times 1, and our new entry would be 2. Then we'd have 2 times 2, so that entry would be 4. 2 times 3, and that entry would be 6. And 2 times 4, that entry would be 8. And, it doesn't have to be a nice whole number. We could do this same exact process. We could, in fact, let's use the same matrix. And we can multiply it by, say, a half. All this means is that you're going to take each entry and multiply it by that constant. And in this case, we're going to do 1 times 1/2, so that entry is 1/2. 1/2 times 2, that entry becomes 1. 1/2 times 3, so we get 3 halves. And 1/2 times 4, and that gets us 2. You can also, we are going to talk about subtraction, but you can think about subtraction as multiplying by a constant as well. We could take our same matrix and we could find what's negative times that, or -1 times that. That is the example of how subtraction is going to work here with matrices. And again, you just multiply each entry by that number. We can add and subtract matrices with each other, but it's really important to pay attention to the size or the dimension of the matrix, because when you add and subtract matrices, they must have the same dimensions. You're going to see why in just a second. So I'm going to make up a couple matrices. Let's have a matrix 1, 2, 3, 4, 5, 6, and we'll call that matrix A. And then let's have matrix B, and matrix B is going to be 7, 8, 9, 10, 11, -5, just to mix things up a little bit. Now matrix A and matrix B both have the same dimensions. They are both 2 rows and 3 columns, so they are 2 by 3 matrices. Now we can find the sum of these 2 matrices, A plus B, by adding corresponding parts or entries. So if I were going to add matrix A and matrix B, I would just take matrix A, add matrix B, and we would just add the corresponding entries, which means, hey, there's 1, 1, there's 1, 1. We add those, and that's going to be 1, 1 in our new matrix. So the new matrix has an entry at 1, 1, that's 8. And then we would do the same for all of the rest of the entries. Here's the entry at 1, 2. Here's the entry at 1, 2. So in the new matrix, our entry at 1, 2 is 10. Here we have 3 and 9 in the same location, so that is 12. Here we have 4 and 10, so that one's 14. 5 and 11, so that one's 16. 6 and -5, so that one's 1. And there we added the matrices. Subtraction is the exact same thing, except that we are subtracting the corresponding entries. So if we were going to do A minus B, we would just need to subtract the corresponding entries. So we know that our problem is going to have a 2 by 3 matrix at the end because that's what they started with. And again, you're just subtracting. I'm not going to write out matrix A and B again because we have them written down several times. We're just going to carry out the subtraction. 1 minus 7 is negative 6. And 2 minus 8 is negative 6. And 3 minus 9 is negative 6. And 4 minus 10 is negative 6. And 5 minus 11 is negative 6. And 6 minus negative 5 is 11. So there we have the subtraction of A minus B. And one thing it's important to note, though, is that the order you do this in matters as for subtraction. Because if I were to do B minus A, I would get a whole different matrix. Now, adding, you can add in any order you want, but subtracting, you need to be really careful. If it says find A minus B, you need to find A minus B. So just to see some more examples of how to use scalar multiplication, adding, and subtracting, I have some matrices here that we're going to use to find some sums and maybe even find some addresses and things like that. Now, when I'm doing any matrix problems, the first thing I always do is look at the dimensions. That way, right away, I can tell if I cannot do something. So I know that A has 2 rows and 2 columns, so it's 2 by 2. B is 2 by 3. C is 2 by 2. And D is 2 by 3. So right away, I know that if I'm going to do any adding or subtracting, I can only put A and C together, and I can only put B and D together. I can't mix them up. So if we were asked to find the sum of B plus C, that is not possible. Because they have different dimensions. Now, we could, let's say we wanted to do C minus A. That one's definitely possible. What we're going to do is take the matrix C, 1, 4, negative 2, 3, and subtract the matrix A, 3, negative 2, 1, 0. And again, that order matters for subtraction. So now we just look at the corresponding parts. We go, okay, well, we're going to have the address 1, 1 and subtract the address 1, 1 to get our new 1, 1. So 1 minus 3 is going to get us negative 2. 4 minus negative 2 is going to get us 6. Negative 2 minus 1 is negative 3. And 3 minus 0 is 3. So our subtraction yields us a new matrix that's also 2 by 2, and it's negative 2, 6, negative 3, 3. We can also kind of put together all of the stuff that we've been talking about. We can put together our scalar multiplication, our adding, and subtracting. So we might have to find 2D plus 3B. What that means is that we need to find twice matrix D and 3 times matrix B, and then add those two things together. So I'm going to start out with 2D, and that's what I'm going to do first. 2D, I would multiply all the entries by 2. So we would have 4, negative 4, 6, 2, 0, and 8. And then we're going to add that to 3B. So let's find 3B. That would be 12, 21, 6, 15, 3, and negative 3. Now, you'll note that both of these are the same size, and so this problem is actually possible. We can find the sum of these things by just adding them together. So, corresponding entries get added with corresponding entries, and we have 4 plus 12, 16, negative 4 plus 21, which is 17, and 6 plus 6, which is 12, 2 plus 15, which is 17, 0 plus 3, which is 3, and 8 plus negative 3, which is 5. And that would be our problem, 2D plus 3B. Just because some matrices have the same dimensions doesn't mean they're always the same. However, we can look at equivalent matrices if we are having some unknowns. So here I have two matrices. I have matrix W and I have matrix X. And if we looked at the dimensions, matrix W has 3 rows and 2 columns, so it's a 3 by 2 matrix. And matrix X is also a 3 by 2 matrix. Now if I were to say that these two things were the same, if I were to say, okay, W equals X, then we're able to identify some of those unknowns. When you have equal matrices, what that means is that the entries are equivalent. Corresponding entries are equivalent. So if we were to look at matrix W, and we looked at the 1, 1 entry A, and if it were equal to X, the 1, 1 entry of X would be that, so A would equal 5. And we can do the same for all the rest of them. Here we have 7 at the 1, 2, and F at the 1, 2, so F equals 7. And B would have to equal 4. And C would have to equal -1. And E would equal 0. And D would equal 9. Now, I only know that these were equivalent because I said they were equivalent. Just because they have the same dimension, that doesn't mean they're the same. However, if they are, then you can say that corresponding entries are equal. This is especially handy when we're solving and when we're using these matrices to do certain things and find other unknowns. So here, look at all that stuff we were able to identify as soon as we said that they were the same. So here we have another couple of matrices, and these matrices are equivalent. Right off the bat, I'm going to notice that they are both 2 by 2 matrices. They both have 2 rows and they both have 2 columns. Now, because these are equivalent, I know that the corresponding entries are equivalent to each other. So I know that 12 over 2 has to equal 6. And, well, that's true. 12 divided by 2 is 6. Now, if we wanted to identify our unknowns here, I see that I have 3x minus 1 in the entry 1, 2. And I have -2 in the entry 1, 2. Since I know these matrices are equivalent, I know that 3/2 x minus 1 is equal to -2. So now I can solve for that unknown. And we just solve that by undoing. So 3/2 x equals -1. Multiply by the reciprocal. So we get x equals -2/3. We can do the same. We can use the same process to identify y. So here I see 4y plus 5 is in the 2, 2 entry, and I see that y minus 7 is in the 2, 2 entry. Since these are equivalent matrices, I can say that 4y plus 5 equals y plus 7, and now it's just a matter of solving. So we can use our basic solving linear equations knowledge. So we get 3y plus 5 is equal to 7. Subtract 5 from both sides, so we get 3y equals 2. And divide both sides by 3, so we get y equals 2/3. So we were able to identify both of our unknowns because we knew that these were 2 equivalent matrices, which meant that each corresponding part was the same. So just to practice that a little bit more, we have one more set of equivalent matrices. Again, these are both 2 by 2 matrices. And again, the corresponding parts are the same. I can see that right away by going, hey, those are both 3, and those are both 5. So in order to find my unknowns, I just need to look at 2x minus 5 being the same as 12, and 2y plus 10 being the same as 4y plus 19. So it's just 2 equations that I need to solve in order to find my unknowns. So let's start with x. 2x minus 5 is equal to 12. Then I'm also going to have to do 2y plus 10 is equal to 4y plus 19, because those are the equivalent entries. Now, just a matter of our undoing. Here, I'm going to add 5 to both sides. So we get 2x equals 17. Divide both sides by 2, so we get x equals 17/2. Then, if we looked at our y component, Well, we need to gather everything, y's on one side, numbers on the other, because I want to keep things positive. I'm going to move these two y's. That way I get 10 equals 2y plus 19. Now, since I decided I was going to put my y's on the right, I got to move my numbers to the left. So I'm going to subtract 19 from both sides. Get negative 9 equals 2y. Divide both sides by 2. And y equals negative 9 halves. Now that we've sort of gotten the hang of how to do some basic calculations with matrices, we're going to talk about a couple of handy matrices as well as some other tips to remember before we move into our little recap bit. So we know that if we took a number, like let's say 5, and we added 0 to it, we would still have 5. 0 is what's known as the additive identity. Now, there's an additive identity with matrices as well. And the additive identity matrix is just a matrix that's full of zeros. And its size is just determined by whatever the matrix you had. So if you had let's make a 1 by 2 matrix, and we wanted to ensure that we kept that same matrix, what we would add to it would be the additive identity matrix, which in this case would just be 0, 0, a 1 by 2 matrix of the same size. So that's something that, comes in handy every once in a while. Another important matrix is the multiplicative identity. So let's say we have the number 5, and we would think, what would you multiply 5 with to make it stay 5? And that would be 1, and that is known as the multiplicative identity. The multiplicative identity in a matrix is one thing that's important to note is that you can only have that for square matrices. What do I mean by a square matrix? That means that the number of rows and the number of columns are the same. So I could have a 100 by 100 matrix. It would still end up being a square because the rows and the columns are the same. Now the multiplicative identity matrix is going to be a matrix with 1s along the diagonal and 0s everywhere else. When we talk about multiplying matrices, you're going to see how this matrix works and how you multiply it with another one and just end up with that same matrix you started with. And I just wanted to introduce this now since this was kind of easy stuff and the multiplying one is going to get crazy. But these are, a couple of handy matrices that you might use more than once, especially, like I said, if you're going to be doing some coding. So those other tips, I guess I'm going to have to put those on a separate slide. I'm writing too big. So we had two special matrices that we used on the other slide, the additive inverse and the multiplicative inverse. We're going to talk about one other special one before we move on to our tips. So let's say we had the number 5, and we wanted to know what would we add to 5 in order to make it 0? What do we have to do to undo having 5? Well, in this case, it would be negative 5. And that is what's known as the additive inverse. Now, matrices have additive inverses as well. So if we had, let's say, the matrix 1, negative 2, 3, negative 4, we would go, okay, well, what do we need to add to this in order to end up with a matrix that's 0, 0, 0, 0? Well, basically, we're just looking for the inverses of all those. So this would be a negative 1, that would be a 2, that would be a negative 3, and that would be a 4. So this matrix right there is the additive inverse of the original matrix that we started with. Now, we did some adding here, so here's a good place to note. Now remember that addition with matrices is commutative. So what does that mean? That means that I could take A and add it to B, and it would be the same as taking B and adding it to A. Now, it's important to note, though, that a subtraction is not commutative. So that means that A minus B is not the same as B minus A. Now, occasionally you might have some weird matrices where it works out that way if you had like all zeros in your matrices, but subtraction is not a commutative property. And you actually know this from just thinking about regular numbers, how numbers work. That's why these things are not commutative. Another thing that you can note is that addition is also associative. That means you can do some addition and then add something on later on. Or here, if we look at it algebraically, let's say we had matrix A plus B and we added those together. And then we decided, hey, let's tack on matrix C. Well, that's the same as if we had, oh, let's do B plus C first. Oh, and then I guess we should add A. So that's what it means by addition is associative. So you need to be especially careful when you're doing subtraction, but for addition you have some flexibility in the order in which you do some of the things. Those last little examples made me think about how much our adding and subtracting matrices really rely upon our being able to add and subtract just simple numerals. So I wanted to look at sort of one big example before we finish up. So here I have, let's call this matrix A, let's call this matrix B, and they end up making matrix C. What we have right here is simply a statement that says 4 times matrix A minus matrix B is going to give us matrix C. So we can think about what we learned. First off, the order matters. I can't flip it and do B minus 4A and end up with C. And we can also think about the fact that those corresponding entries are going to be equivalent. So I know that if I take the entry at 1, 1 in A, and I multiply it by 4, I'm going to have to subtract the B11 entry, and that's going to get me the C11 entry, and so on and so forth. So for this one, it looks like what we want to do is find x. That's the only thing we don't really know. So if we take this into consideration, we know that 4 times the entry A12 minus B12, which is where the x is going to get us C12. So let's go ahead and actually do that. We know that 4 times negative 2 minus 2x should get us negative 12. See how all those are coming from the corresponding entries. They're all in that 1, 2 position. Now we just need to really solve this equation. We're going to end up with negative 8 minus 2x is equal to negative 12. Now we just need to solve, so I'm going to add 8 to both sides. So we get negative 2x equals negative 4. Divide both sides by negative 2. We get x equals 2. So that means if we were to plug that number in and actually do that calculations, we would end up with equivalent across the board. So let's actually do that. If we know that x is 2, we would know that 4 times negative 2 minus 2 times 2 is equal to negative 12. So that would be negative 8 minus 4 equals negative 12, and that's correct. So we could see the power of these matrices. We were able to find that variable and how those corresponding parts relate to each other. So just sort of to sum up all the different things we did in this video is we started out by looking at a matrix and defining that matrix. Remember that matrix, let's call it matrix M. Sorry, I made you wait. Has entries in it, and each of those entries has a particular address. Remember that your matrix has dimensions that are always rows by columns. So in this case, it's a 2 by 3 matrix. And each of those entries have an address based on the row they're in and the column they're in. And we can do things with matrices. We can use scalar multiplication. which means multiplying it by a number. And all that means is multiply each entry by that number. And then we were able to also do some addition and subtraction. And we knew that addition we can do in any order, but subtraction, the order really matters. So you might as well just get used to doing it whatever order it's listed in for adding and subtracting. But remember, for adding and subtracting, they have to be the same dimensions. This means if you have a 5 by 5 matrix, you can only add or subtract it with another 5 by 5 matrix, because your answer, your solution, is going to be yet another 5 by 5 matrix. Now 5 by 5 matrices reminds me of something else. 5 by 5 matrix is a square matrix, and that related to those fancy matrices we talked about, or those special matrices with the additive identity and the additive inverse. And those are things you just want to keep in mind because they're going to make some of your calculations a little bit easier. Sometimes you can tell your computer, hey, take the additive inverse of that. And now you'll kind of know what it's doing. And then we also talked a little bit about equivalent matrices. And that just means that the corresponding entries were the same. So that just sort of looks at everything we did with our matrices. They're really not too bad once you get the hang of them. And once you start doing them by hand, you'll be able to apply that into some computer or other technology that you might be using. And you'll be able to see where you use those. In fact, if you looked at some code sometimes for some of the games you play, or for some of even the websites, you would see examples of these arrays used quite a bit.